Yeah, I noticed that. I had started the recording, but for some reason it stopped.
Okay, thanks, Jordan. We'll get it going here. Okay, I think it's now recording. There we go. Okay, thank you. Kirchhoff's voltage law states that the sum of the applied voltages equals the sum of the volt drops. And in this case, the applied voltages are the 20 volt and the 5 volt. The volt drops are VR2 and VR1. Because we established the direction of current, we can very importantly, this is very important, show the plus and the minus here. Since current's flowing in this direction, we know that current leaves the plus of the dominant battery if they're opposing. Current leaves the plus usually of the battery. If they're opposing here, we have a unique case where current's actually charging the second battery. Current's actually charging the second battery because they're opposing, but current flows in this direction. Current enters the plus and leaves the minus of all the volt drops. And we have to indicate that. That's up to you to put in. We also don't want to worry about ground right now or common. That's just a place we reference. We call zero, we measure from. Current, and this is hard for people starting a circuits course to realize that current ignores ground, doesn't care. Unless there are multiple grounds, then there's actually a wire there, so it could flow through. But with one ground, current just ignores ground. And this tells us that the sum of applied voltages, which happens to be 15 volts, is dropped across R1 and R2. With that knowledge, we can figure out the current, because we know that 15 volts is dropped across R1 and R2. That's 15 divided by 2K, giving us our current 7.5 milliamps. Once we know the current, if we know any resistor, we can multiply the two and find the volt drop. Same thing over here, 7.5 milliamps, multiplied by 1K, 7.5 volts. We now have all the volt drops in the circuit. We have a 20 volt drop across V1, a 5 volt drop across V2, 7.5 volts dropped across R2, and 7.5 volts dropped across R1. We know all the voltages, all the volt drops. So we could start at 0 and we can work our way up towards what we're looking for, Vx. We can go clockwise or counterclockwise. We can go with the current or against the current. It doesn't matter. We should find the same answer. So when I solved this, I went against the current. Well, first, okay, I'm saying there's 7.5 volts. What I did is I started at 0. I went up 7.5 volts, which is VR2, 7.5 volts. And then I went up another 5 volts, bringing me all the way here to 12.5 volts. And that's Vx, 12.5 volts. To check that, we could go the other way, where we actually drop, going from plus to minus. We start at 0 and we drop 7.5, putting us here at a negative 7.5 volts. And then minus to plus, we're going up 20 volts. Minus 7.5, go up 20. We are now at 12.5 volts. Checks out. So our math must be correct. I've updated the PowerPoint to add this to it. Actually, so if you re-download the PowerPoint, you will get this. Any questions about this slide? It's a little bit challenging with the resistors under the batteries. I'm much more comfortable with the resistors above. We had to. This was kind of our stretch, our being able to apply Kirchhoff's voltage law and say we're applying 15 because it's 20 opposing 5. Thus, a 15 must be dropped across those resistors. 15 must be. Yes.
I guess it's funny. This almost looks like the one on the assignment, except one of the batteries are flipped.
Yep. Oh yeah. Yep. Our assignment is practice for this. Who won the prize? Somebody's asking. That was Mr. Irving. Mr. Villagas Irving won the prize, I do believe. Regrettably, it's not a big prize. I'll shake your hand when you come. Maybe once we get here, it'll be easier to give prizes, or some instructors give bonus marks, and we'll see. With this fresh in our minds, I'm going to maybe try and challenge you with part 2. I'll move the resistors back up where we're used to seeing them, up above. We'll even put our circuit common down below where we're used to seeing it. But we're going to dangle this R3 up here in by itself, and I'm going to ask you, what is Vx? And maybe we'll pause for a couple of minutes to see if anybody can come up with a quick answer here. Our second prize. Anybody have a solution? Anybody want to hazard a guess?
Is it minus 12 volt?
No. No, that's not the correct answer. Guess?
Minus 14, right?
Uh-huh. We're getting in the ballpark here. We're getting closer, but I don't like that minus. Let's say you have half of the answer.
Here we need
It's
to
14.
apply node voltage.
Yeah, we're okay. So
Can we consider 2 node here?
No. No, that'll be next chapter. We'll look at nodes. We don't need that here. I think it was Jade that gave the answer. And we're going to go through it here. So let's go through it. Once again, we look. So you mentioned nodes. First, we want to determine, are there any resistors that are in series or in parallel? And that's going to be the tricky part. Maybe I'll postpone that for a minute. I'm going to look at the 2 batteries, and it does appear that these batteries are not in agreement. They are opposing. So it does appear that we have opposing batteries, and usually unless we have a really strange circuit, the larger battery will win and most likely charge the smaller battery. And let's trace current flowing through here. If we go with opposing and the larger one wins, and that we don't have something really tricky like next chapter, what will happen is current will flow from the larger battery, cause a volt drop across this resistor. The current encounters a node or junction, and here the current has to decide how much will flow this way and how much will flow this way. We could use current divider, and it will follow the current divider principles. However, our keen powers of observation note that there is no connection at this point, other than a voltmeter, and a voltmeter, if it's a good voltmeter, is an infinite resistance, meaning no connection. Another word for no connection is open circuit. So at this point, we have an open circuit. We know that through an open circuit, at an open circuit, there will flow 0 current. That is one of the definitions of an open circuit, no current. So no current. That makes our decision very easy. All of the current will flow through R1, causing a drop. It comes through and charges the 6-volt battery. The current continues. The pressure or the voltage is pumped back up by our big 18 volt, and the same current carries through. Since it's the same current, this must be a series circuit. There are no parallel branches. At first, it looked like R3 might be a parallel branch of some sort because it branched off, but because it's an open circuit, there is no current flowing through it. Therefore, it does not have any impact on a circuit. It might as well not be there. The volt drop across R3 is equal to I3 times R3, and that would be 0 multiplied by 3K, giving us 0 volts. There is no voltage dropped here. No current, no voltage. We do not have to concern ourselves with it. Well, we could redraw this equivalent circuit. Our textbook likes to do that. I prefer just to kind of put on my detective hat and see what maybe I know enough information that I don't have to redraw it. If I start at 0 and go up 6, this point must be at 6 volts. If I start at 0 and go up 18, this point must be at 18 volts. And I can see here that from the 6 volts to the 18 volts is dropped how much voltage? What is, pardon?
12.
12? Thank you. 12 volts. So from 18 to 6 is a drop of 12 volts. This 12 volts is dropped across 6K, a 2K and a 4K. R3 does not contribute anything. No current, no voltage. It's just there, maybe as a trick. And so we can figure out I as the total applied voltage divided by the total resistance through which that voltage is dropped, which is 2K plus 4K. So we end up with 12 volts divided by 6K, giving us 2 milliamps of current flowing. So Matthew, I think your microphone keeps turning on here. Keep turning off your mic here. So if anybody leaves their mic on and gives feedback in the circuit here, in our electrical audio circuit. So the 2 milliamps is our current flowing. It's a series circuit. It's 2 milliamps everywhere in that circuit, almost everywhere in that circuit. Down here we have 0, but all the other currents are 2 milliamps. Knowing that current, you can't resist. You have to 2 milliamps times 2K. When you see current entering a resistor, multiply them, it will give you the volt drop. 2 milliamps flowing through 4K, 2 times 4 is 8. K times milli cancel out. Ohms times amps gives you volts. So I have 4 volts, 8 volts. Once I have the volt drops, I can determine the voltages with respect to ground by traveling through the circuit. 0, go up 6, I'm at 6 volts. Minus to plus, I'm going up 6, go up 8. This must be 14 volts. To make sure I did not make a mistake, I'll start on this side, 0, go up 18, I'm at 18 volts. 18 plus to minus is going down. 18, go down 4, I'm at 14 volts. So this line, and let's change our ink color to make sure we get this. Okay, mouse. Pointer options, ink color. Let's. Yeah, I'll pick red. So this electrical point. An electrical point includes all the lines without crossing a component, all the wires without encountering a component. So in red here, this point is at 14 volts. X is down here. We do indeed cross a component. If we cross a component, we're traveling through the circuit. We start at the voltage that we're at, and we must drop or go up the amount of voltage that we encounter as we go through a component. So here it looks like we're going from plus to minus as we go through R3. So we're going to drop. And how much voltage are we going to drop? We're going to drop 0. So 14 drop 0. Vx must be 14 volts. So we're going to measure here. Our multimeter will measure 14 volts. It says point X is 14 higher than ground. Now, what's a little tricky is we could move this wire and bring it up here, and we would also measure 14. So these 2 points are at the same potential, at the same voltage. The reason that is because there's no current flowing. When there's no current flowing through a component, there's no volt drop, and they remain at the same voltage. That's another tricky concept.
Question.
Yes.
So it's almost like, because it's not connected anywhere, it's still part of the node as per voltage. It's like it has a potential that if it connects somewhere, it's this potential. I don't know if that makes sense.
So what's node? Is our textbook talking about nodes?
Well, we crossed it in engineering software.
Oh,
The one node is where there's one voltage, like where the voltage doesn't change because it's between in between components.
An intersection of components. Yeah. Yep.
One question, Ray.
Yes.
When I connect the voltmeter, the current doesn't start to fluid in this point?
No. Because the multimeter is a good multimeter and it's set to voltage, it has a resistance of infinity. It's a good question. Get a resistance of infinity. Let's see if we can look at that a little bit here. I'm gonna slideshow from current slide. Okay, let's see if we can expand on that a little bit. And that will bring us kind of leading on to the end of the chapter. Okay, if I had 120 volts, big battery, I'm going to put a resistor here to simulate, just to make us think a little bit, maybe 100 kilometers of wire, and it's got some resistance. And I'll say maybe it's about 100 ohms of resistance. And then I'm going to wire. So again, be careful. Don't do this at home. But I'm going to wire these to 2 little plugs here. And all right, we're going to set this to voltage, and we're going to connect 2 wires. And I'm going to connect one of these wires over here, the other wire over here, and see if I can measure the voltage. Now, because I bought a very good multimeter, inside the multimeter, there will be a resistance, and this resistance, Rm, I'll call it Rm. Rm for a good multimeter is very close to infinity. What that means, let me redraw my circuit without the fancy plugs here. 120 volts. 100 ohms. In the circuit I'm showing, I equals 120 volts divided by 100 ohms plus the resistance of the air. And the resistance of the air is infinity. So we end up with 120 volts divided by infinity, giving us 0 amps. So I equals 0 amps. Air is very high resistance. If it's a foggy St. John day, the resistance could drop to a few mega ohms, and then we might see some sparks. Have you ever walking down the street and you hear some little sparks coming from the power lines up above, especially on a humid day? Maybe the air resistance has dropped a little bit. But we tend to think of air as being infinite resistance, and when we divide by infinity, we end up with 0 current. Then we decide to hook up our voltmeter to measure the voltage. If we have a very good voltmeter, the resistance of the meter is also infinity, and the current remains at 0 amps. And we will be measuring 120 volts because the drop across the 100 ohm resistor, the internal the resistance of the lines or the wires, is 0 because Ohm's law says 0 amps multiplied by 100 ohms, 0 volts. And we are measuring 120 volts because we purchased a very good voltmeter. But maybe we're out of money and our friend has a very cheap voltmeter that he wants us to use, and we decide to use the cheap voltmeter. Voltmeter not good. So if we decide to use a cheaper voltmeter and hook it up over here, and maybe this really cheap voltmeter has an internal resistance of 100 ohms. But we remove this one. We put a voltmeter of 100 ohms. Well, what we're doing is putting 100 ohms in series with our circuit. So now instead of infinity, our cheap voltmeter has an internal resistance of 100 ohms. We now are getting some current. We're actually getting a considerable amount of current. We're getting 60. What are we getting? We divide it by 2, we get 60 milliamps. We are getting 0.6 amps of current. And now that means that we're going to get 60 volts here. 60 volts dropped across the meter, and our voltmeter will measure wrong. Our voltmeter is going to say 60 volts instead of 120, because now current is flowing, causing all kinds of volt drops everywhere. That's why we need a good voltmeter. If you use a good voltmeter, we will be measuring here 120 volts because I equals 0, and so there's no drop here. Having said that, let's say I decide, I lost my pen here. Let's say I decide I want a cup of tea. Draw a spout here. I want some tea, so I'm going to plug in my kettle. I'm going to plug in my kettle. Now current will flow into the kettle, heating up the element. Current flows back. How much is the element in my tea kettle? Well, if the element in my tea kettle happened to be maybe it's a 1 kilo ohm. Or the tea kettle is 1 kilo ohm, and we're going to use voltage divider, and 1K divided by 1K plus 100 times 120. This might drop maybe to do it 1,000 divided by 1,100 equals times 120. It's going to drop down to 109 volts. What? So when I plug my tea kettle, voltage drops from 120 to 109. That's called loading. We load down the circuit. A good voltmeter, a very good voltmeter, I keep putting dollar signs, has a resistance of infinity and will not load down the circuit. A poor voltmeter, a cheap voltmeter, has a lower resistance, could load down the circuit. A tea kettle certainly will load down the circuit. It's a load. A motor, anything you plug in will cause the voltage to drop slightly if it's a good system. If too many things are plugged in, we get what's called a brownout. We might drop the voltage too much and cause a power outage. But these, if you have hundreds of kilometers of wire, of cable through a city, it does have some resistance. And when current starts flowing through that resistance, we have some volt drops. So that was a good question you asked about a meter completing the circuit. The meter should not complete the circuit. Our meter should not complete our circuit. So if I have in this circuit 12 volts, 6K, we have I equals 12 volts divided by 6K, giving us 2 milliamps. 2 milliamps flowing through 2K gives us a drop of 4 volts. The 2 milliamps carries on. There's no connection here. 2 milliamps carries on and giving us a drop here of 8 volts. So we have 8 volts from this point to this point. If we were to add a resistor here with no connection, that's an open, the current is 0. So the volt drop is 0. And we still have 8 volts here. If you then hook up your meter to measure voltage, a good voltmeter has a resistance which is very close to infinity. So I remains 0 and things stay the same. Now, if you buy a cheap meter, and so that I can do the math in my head, I'm going to pretend it's a multimeter that has a resistance of 4K. And sorry, I'll pretend it's got, maybe it's got 3K and this is a 1K resistor. Well, if I connect that meter, as soon as I connect meter, I'm putting 3K, the resistance of the meter, in series with this 1K, and all of that's in parallel to 4K. I change the whole circuit, and I'll get to the question here in a second. But so I'm going to change that whole circuit. I'm now putting the 3K in series with the 1K. So effectively, what I've done, I'm going to have to redraw it over here. I have a new circuit where this 4K now has in parallel with it a 1K and my meter, which is 3K. And so the equivalent circuit, we've got our 2K and 4K in parallel with 4K, because this is indeed 4K. 4K in parallel with 4K is 2K. And my current is now 12 volts divided by 4K, or 3 milliamps. So by hooking up a cheap, no good meter with an internal resistance of 3K, then I'm going to change this current to be 3 milliamps because I'm putting stuff in parallel. I'm loading down the circuit. If this becomes 3 milliamps, then this becomes 6 volts, and this becomes 6 volts. Or does it? Wait a minute. Yeah, it does. It has to. That becomes 6 volts. And 6 volts divided by 4K means that I've got 1.5 milliamps here. This becomes 1.5 milliamps. And so I end up with a 1.5 volt here. And this becomes 4.5 volts. We changed the whole circuit. We made a lot of work for ourselves. So now we measure 4.5 volts instead of 8. Oh no. Oh no. Get a good voltmeter. Question. I see here quite a few questions. Now let's go with Joe.
Yeah.
Joe's Soto, please, first. He's got the first hand.
Yeah. Hello, Ray. Regarding the good voltmeter, you say will be almost infinite resistance, but what would be the actual value?
When you purchase a voltmeter, it will come with a manual and it will tell you the actual value. And so I've seen, I see some of around 10 meg, maybe 2 meg to 10 meg. So it depends on the meter. If you're into the mega ohms, I think we're okay. I don't want you to spend $1,000, but a $5 meter probably will be no good in January. The ones we're recommending in Canadian dollars, they're in the maybe $40 Canadian, just to give you an idea, but we'll
okay,
talk.
But sorry, but we cannot find, for example, giga ohms internal resistor multimeter, right?
I'm not sure. If you want to pay a lot of money, maybe.
Okay, thanks.
Yeah, a lot of money. And And we have Louis.
Ray. Actually, my
best choice.
I have to mute Mr. Hossein here. So Louis?
Oh yeah, hi Ray. Actually, my question is not regarding this, but regarding the previous circuit. Can I ask about that, or shall we finish this?
Yeah, maybe if you don't mind waiting till we finish, and then I'll get back to you.
All right, no problem.
Just because I'll lose the information here. And
Sure,
we have
sure.
Ricardo Martinez.
Yes, sir. It's regarding with the multimeter.
Yes.
In my case, this resistance in the data sheet is the same as the input impedance. Okay.
Yeah.
Okay. Okay. Thank you.
Okay, you're welcome. So anybody else before we get to Louis' question about the previous slide? Okay, let's see. This slide, Louis?
Yep. Yes, sir.
Okay.
So, okay, my question is, if let's say we connect the dangling wire to the ground, and we are asked to find PR3.
I got to stop you right there.
Yeah.
It's a very good question, but if we were to connect this to ground, then we would ask, are any resistors in series? And the answer would be no, because different currents flow through these resistors. There's a node or a branch here. Are any in parallel? To be in parallel, each side must be connected together, and there's a battery in between, so there's no parallel. So we have three resistors. They are not in series. They are not in parallel. Oh no. We are in chapter 8 and 9. Chapter 8 and 9 deal with circuits where the resistors are not in series and they are not in parallel. Maybe we don't want to think about that quite yet. Right now, we are getting comfortable with series, parallel, and series parallel combinations. But regrettably, there are those circuits that are not in series and not in parallel. This is one of them, and I will start when we get to chapter 8. I will be starting with this circuit.
Okay, because I asked about that because in assignment number 23, it looks like the same connection. I mean, it's somehow.
Now in 23, there is, when you rearrange it, you'll see that we can indeed come up with some resistors in series and parallel. I can, near the end of this class, in about 15 minutes, I can have a look at number 23 if you want.
All right.
Okay, if I forget, remind me. We'll look
Sure.
at 23.
That's right. Yep.
So this, that's chapter 8. So right now we just want chapter 6, 5, 6, and 7. That's our test next week. We'll be on 5, 6, and 7. Not next week, but in about 9 days.
Sorry, was that a date for the test?
Oh, you don't. You should have a date for the test. I think. Let me confirm here. Brightspace.
I wasn't sure if I heard you say a test or assignment.
Yeah, I did say test. And so if I look at due dates, your Brightspace, you should see something similar to this. if you click on due dates and summary, there's a file there, and it says, look at this, test number 2, November 16th.
Nice. Okay.
So this is a summary. It's subject to revision, but right now we are, we could even possibly be ahead of schedule. Things are looking good for the test at that point, unless you want it a bit earlier. But the assignment is due November 12th. I guess Jeff's intent was to give some time to mark the assignment before the test, but I know I'm going to post solutions for the assignment, and we can go over any questions you might have about it. But we'll see. Right now, it's tentatively scheduled for November 16th, our test.
Hi, Ray. I got a question about the value of Vx. So how do we know that 14 volts is positive? I got confused with that.
Again, we've got to travel through the circuit. We establish first that they're opposing, so this one pushes more. That gives us these drops because current is flowing in this direction. Our first dilemma is this open, and that simply tells us that this current is 0, and thus this volt drop, which is the current times the resistance, must be 0. Since this current is 0, then all of the current flows into the 4K resistor charging the battery. Once we know that, I tend to want to just start here at my 0 volts and travel through the circuit. If I go up 18, then this must be 18 volts. And if I go up 6, then this must be 6 volts. And so I can see here that there's 12 volts dropped across 6K. From this point to this point is a total of 12 volts. From 18 to 6, it's a drop of 12. And this drop of 12 volts is across the 6K. So that gives me my I here as 12 volts divided by 6K, or 2 milliamps. So I have 2 milliamps of current here flowing. The 2 milliamps times 4K gives me my 8 volt drop. 2 milliamps times 2K gives me my 4 volt drop. And then I go back to traveling the circuit. 18 volts, drop 4. I must be here at 14 volts. Or if I want to go the other way, 6 volts, go up 8. I'm at 14 volts. I continue traveling through the circuit, 14 volts, drop 0. I'm at 14 volts. So it is indeed a positive. If either battery was reversed, I might get a negative. I could also get a negative by moving my ground somewhere else. But in this circuit, I see each battery brings the voltage up, and all we can do is travel back to ground. So there are no negative voltages with respect to ground here.
Okay, thanks.
You're welcome. Last class, somebody asked about this 3-dimensional hard on the head circuit where one of the branches is coming out of the paper towards you. And all I can tell you to do, may take a bit of practice, but maybe using different color pencils might help as well. If you picture here the red kind of coming out of the paper at you, then we could make this a hinge, and we could rotate this, kind of take it and move it to flatten it out. And the other thing that helps me is if the circuit has no labels, I add labels at certain locations, and then I make sure that when I redraw my circuit, those labels make sense. For example, I make sure that between the 6 and the 3 is Y. Y is between 6 and 3. I make sure that my Z over here has a 3 on kind of on the top side and a 6 beneath it. So I see here my Z has a 6 beneath it and a 3. And then I show all the, if I show this in color, then I can use a colored pen to show how I actually took the circuit that was over here, and we kind of swung it on hinges. We moved everything over. And we're allowed to do that as long as we do not cross over any components. Any questions about that? I heard of a school a long time ago that would take applicants to take the course, and it was actually not electrical and electronics, it was a mechanical engineering school, and they would ask the prospective students, here's a drawing, can you visualize in your head moving things in 3 dimensions? And that was a prerequisite. They would make sure that you could visualize things to take the course. That's not a requirement here, but it would certainly help in doing this. If you are not able to 3-dimensionally rotate things in your head, and not everybody can, it's a tough concept. If you're not able to do it, then I recommend using colored pencils and showing in different colors each part of the circuit. And I've seen a lot of people get through doing that. They show each different branch in a different color, and then when they redraw it, they travel through the circuit, and in purple, connected to the 18-volt positive. In purple, I have a 6K, and on the other side of the 6K, I have point Y, and then I get a 3K, and then on the other side of the 3K, I return to the negative, and then I'll switch back to my red, and I see here that at the positive, I go to 3K, so at the positive, I go to 3K, this 3K, and at this point, I actually go to Z. And after Z is a 6K. And I'm starting to get lost, so I'm going to give this a label. I'll call this, I'll call it L because I'm getting lost. L, and then from L, I go to the negative or common. That's right there, negative. And I've redrawn the circuit. And this way, I'm not 3-dimensionally rotating things. I'm just redrawing them with different colors and making sure that the connections line up. And something else that might have helped is to call this RA, RB. That's RA, RB, RC, RD, RC, RD. Don't be afraid to label things to help you redraw them.
Where is X?
X. Okay, I'm going to use a good question. I'm going to use green to identify X. I did not show X. So X. X connects to three things. X connects to the positive of the 18-volt supply, X connects to RC, and X connects to RA. So X connects to the 18-volt supply, X connects to RA, and X connects to RC. So here in green is X. And I could show it in this other equivalent here as well. X. I think it takes some practice. So at this point, I might get back to Louis' question number 23, which is very related to this. To do that, I need a blank. I don't want to solve it for you though. Louis, is there on 23, is there a specific area you have a concern with, or is it where to start?
I'm actually stuck on that number.
Okay. So maybe I'll do it with different values. $23-ish. I'll change the values. I think that's it there. I'll just make up some values here, maybe. Oh, I gotta use different. Make this 1K. And is that okay? Let me make this 3K. There, we get different value resistors. That's a 1. So I encounter a new circuit. What am I to do? Well, if I look at what section of the chapter I'm at, it might give me a hint. Nah, I'm not getting much hints. Well, are there obviously are there easy to see series or parallel resistors? No. Okay. Are there maybe series opposing or aiding batteries? Nothing obvious. Can I use Ohm's law right away? Is there a resistor across which I know the voltage? Maybe. Do I want to redraw this circuit to make it look easier? Maybe, but boy, this looks like a tough one to redraw right now. So I always like to see, can I use Ohm's law? Especially since this is series parallel chapter, there should be somewhere I can use Ohm's law. So I'm going to have a look at this right now. But in using Ohm's law, I might, time to travel. I want to do a little traveling because this circuit, nothing obvious to me right now. So I'm going to do some traveling. In my travels, let me use a different color. I'll go back to purple here. So if I'm traveling, I'm going to start at the only point I'm very comfortable with that I know right now. That's 0 volts, definitely. Matter of fact, yeah, let's use our color because this is suspicious. Look at this. Wow. This is 0 volts. This is 0 volts. 0 volts. Nice. That should help. This line here is put there to kind of trick us to, maybe not trick us. It's done sometimes in circuit boards where you surround the circuit board with a ground for shielding purposes. But now that I know 0, do I know other voltages? Well, let's change my ink color and try blue here. Well, this 5 volts is a drop of 5 going from plus to minus. So then this point is going to be at what voltage? Anybody tell me? 0.
Negative
5
5
volts.
Negative 5. 0, drop 5. Plus to minus is a drop. Minus 5 volts. So when traveling, you know, colored ink is going to be your friend here. Speaking of, I've got that node. It's since Mr. Parker has introduced the term node, we'll keep with it. And I'm going to change my ink color. Yeah, I'll use red. Whoops. And the only other node is this one, and now I've colored all the wires in, or all the points, and it looks like I can start at 0, and I'm dropping 15, making this point negative 15 volts. At this stage, I would like to wrap my head around this. So to wrap my head around this, I like to show a number line and the voltages involved. Looks to me like there's a lot of negatives involved. So if I start here at 0, I have a -5, and I have a -15, and I have shown the -15 kind of in red, and the -5 over here in blue. And if I go back to, I have a neutral ink color. I'm using a lot of colors. I'll use green here to go from -5 to -15. So I'm going from -5 to -15. It looks to me like I'm traveling 10 volts. So to go from -5 to -15, I drop 10 volts. With the -5 being the more positive than -15. So more positive minus current will then flow in this direction. So I've got 10 milliamps flowing in this direction. Over here, I've got 0, and it drops to -5. So that's an easy one. 0 dropping to -5 is a 5-volt drop. I've got a 5-volt drop. 5 by 2K gives me 2.5 milliamps. Going down here. Do I know any others? How about the 3K? I've got -15 and 0. So 0 is more positive than the -15 over here. So to drop from 0 to -15, that's a drop of 15 volts. So there's a 15-volt drop from 0 to -15. I drop 15 volts. So that is a current of 5 milliamps. The 5 milliamps enters this junction, and 10 milliamps also enters. So leaving here must be 15 milliamps. 15 milliamps loses 2.5. This must be 12.5 milliamps. 12.5 milliamps. Enters here, loses 5. So we must have here 7.5 milliamps. 7.5 milliamps enters this junction. Joins with the 2.5 to make up the 10. Yes. Can we do this in a test? Or in the assignment? Number 23 is different. The batteries have different values. We're going to try it out. Rianne?
With the assignment, can we not use that kind of approach? Because I did something, combination of Kirchhoff's voltage law and Kirchhoff's current law with that.
Yes. Yeah. Well, that's good. The answer is in back of the book for 23. Did you get the correct answer?
I think I got the correct answer, but using a different approach.
Yes. Yeah. There's many different approaches and different orders of doing it, and we could have tried to redraw it as well, but so that is what we're doing. Kirchhoff's current law, we're adding and subtracting currents. Kirchhoff's voltage law, we're adding and subtracting voltages. Ohm's law, I equals V over R. we look for places where we know the voltage, and the trick in this circuit, kind of one of the big tricks was this line here, this line that connected everything together, put ground all around the circuit. I think we've done enough for today before our head explodes. Maybe we'll stop here. I do have one last topic to complete this chapter, and that last topic is ladder circuits, which we've really kind of covered already, but we'll do it in a more formal way next week when we meet again. So meanwhile, I again encourage you to keep working on that assignment, especially because I happen to be one of those instructors who find it hard not to go over an example, not to go over an assignment question. So if you're stuck on an assignment question, bring it up in class. We'll look at it, but you must first try it yourself. First attempt it. You learn a lot more by trying, even if you cannot find the right answer. If you try it first, you learn a lot more than if somebody simply shows you how to do it. So that's the purpose of the assignment, for you to try doing it. And if you're stuck, please bring it up in class. Any other questions before we wrap this up? Nothing. Well, I hope you guys have a nice weekend.
Yeah, thank you, sir.
Thank you.
Nice weekend.
Okay, take care, guys. See ya.
Thank you, Ray. Bye.
Thank you, sir. You too, sir.
Thanks,
Hello,
Ray.
sir.